Hi there. I want to start talking to you about programming. So, if I give you a program like the one on the screen and I ask you, what does this do? Can you tell me? So, pause the video for a sec, think about it, and start it back when you're ready with your answer. So, what does this do? Well, you can see it takes three variables, x, y, and z. Initially, we assign m to be x. Then if m is less than y, we set m to be y. And if m is less than z, then we set m to be z. And then finally, we return m. All right, so what's going on there? Well, if we think of specific numbers, maybe it's helpful. Let's take 1, 2, 3. So if m is initially 1, then here 1 is less than 2, so we'll set m to be 2. Oh, and then if 2 is less than 3, we'll set this to be 3, so we'll return 3. So it seems to be picking the largest number. Indeed, this seems to be the max of 3 numbers. And you can see that this actually works generally, even if they're in a different order. So if I have 1, 3, 2, we'll still be fine, because we'll start off with 1. Then here we'll assign 3, because 3 is bigger than 1. But 2 is not bigger than 3, so we won't execute this statement. So this is actually computing the max. Sort of abstractly, what are we thinking about here? Well, the reasoning, what's actually going on in your head when you think about this program is you start off thinking, well, what is the value of m? M initially is the max just of x. I mean, so it's x. But it's also the max of x. The max of x is just x. And what's happening with each line we execute is we're expanding the scope of the max by one additional variable. So after we've executed line 4, we can see that we've now determined that m is not just the max of x, but it's the max of x and y. And now by taking the max of x and y and comparing that to z, we can determine that on line 7, we have the max of x, y, and z. So all of these things. So that's great. And what's really interesting about this way of thinking about programs is that when you start looking at it this way, really you don't need the code. So what we're doing here is we're initially setting m to be the max of x. Then we set m to be the max of xy. So we're going from max of x to max of xy. We're going from max of xy to max of xyz. And so you can see that the lines of code that I've got in there are simply getting me from one step to the other. So we're establishing the initial premise that m is the max of x. And then knowing that, we can add in y and then correspondingly add in z. And looking at the code in this sort of logical way is actually what your brain is doing when you read code. So if you're actually reading code and genuinely understanding it, then your brain is going through this kind of process. And so being aware of it can be really helpful. So, when we write code, we often want to actually test it. So, I think I just reasoned through this code. I'd like to, I'm convinced that it's correct, but maybe there's a small error, and so it's useful to actually have some tests. So since code is automated, what we can do is we can sort of take this code and we can type it in, and we can sort of see what it does. So I'll just run this and see what the output is. And you can see that it does work. So what I've got here is, in each case, the max is 31. And I'm running 3 different tests for 3 different positions because I want to make sure, that I'm not got some funny little bug. And you can see this kind of test will work. So if I do have a typo, sometimes the code is correct, but, morally correct. But you've got a typo when you entered it, like copy and paste error. This kind of thing is quite common. But what we're doing here is what we call manual testing. So in order to check this, I must visually inspect the output. This is not going to scale. So you can imagine if I have a very large program, checking all these little tests is going to be a big problem. And worse, this kind of testing makes you conservative as a programmer. So, the problem is you run your code, you get it to pass the test. So I'm like, okay, shit, this is not right. I got to get that to be a Z. Now everything's great. Okay, pass the test. And then usually what people do is they don't remember this stuff. They just wipe it out to their test. And they'll just start, proceeding. But now if somebody says, hey, that max function, you could write it a different way. Is that fine? Like, let's say I want to swap these two. I want to put the comparison to Z first. Is that okay? Well, probably. But in the absence of the test, you might be insecure to make this change. So what we say is that the code can become brittle if you have these kind of manual tests. So a better approach is to what we do, what we call automatic testing. So there's a little bit of work here. You can see that there's some stuff I have to write out, but it's in general worth it. So this is not something you probably would have done in your first programming class, because in your first programming class, it's sort of one and done. You write the code, you get it to work, you're done. That's not what we're doing here. So in general, code doesn't work like that. You're usually programming for another programmer. You're writing a program that's going to be around for hopefully many years. And there'll be small changes in maintenance done to the code. And it's important that people be able to develop some confidence that their changes haven't broken anything that you had originally created. So what we'll do is something like this. I'm going to write a test function here called testmax. What testmax does is it takes the values x, y, and z and an expected value. What we're going to do is we're going to run the max function on these parameters x, y, z and see what actually comes out. And we'll check to see if the expected value is equal to the actual value. And if they're the same, well, that's great. We don't need to do anything. Everything was hunky-dory. Otherwise, we need to inform them that the test failed. Right? So in general, passing tests are usually silent because we expect tests to pass. We really only want the squeaky wheel when a test fails. So if you print out stuff for passing tests, you end up with too much noise and it's impossible to tell what's going on. So let's just see what this does here. So when I run this test, you can see, oh, it failed. Why did it fail? I did that intentionally. So this is a failing test. So what it says is here, I was expecting 31, but I actually got 21. And the arguments were 11, 31, 21. So it failed in this case. And just by inspection, I can see what the problem is. There's just a typo there. So if I fix that, then it'll finish the test. This little thing at the end is helpful. If you leave this out, sometimes it's disconcerting because you run the program and you just get silence. Silence is it working? Is it not working? You could have an infinite loop here. So if you just put in some sort of while loop or infinite loop, the program will just hang forever. So you can do something like this. While true, just do nothing. And it's kind of tricky to see the difference between an infinite loop and a passing test. So here you see this little red button here. That's saying that the program is still running. So I can terminate it. But so there you can see the program has terminated now. So you can see that the program does terminate here because it's no longer giving me a red button. We're going to be doing this style of testing in this class because it's relatively light. It doesn't need many tools and stuff. There's a huge amount of frameworks for doing this kind of testing. So you can pick your language, and even for just Java, there's a huge amount of frameworks to do this. The one that I've used in the past is called JUnit. We will use these in later courses at TOEFL, in particular in software engineering. We'll talk about using testing frameworks. But for us in this course, it's just extra weight. We're not going to bother with it. So we're just going to write these kind of manual automatic tests. So I'm going to write for your homeworks, you'll find these test functions. You'll find a main program with tests like this. I've written this function here to take three variables, x, y, and z. I could equally have written it to take an array where I'm just going to look at the three elements of an array. So this is how you do this. And to make things just clear, when I use arrays, I'm going to use doubles rather than ints as the kind of the values of the array. And that's because arrays are indexed by integers. So it's nice to have that contrast between the index, which is an int, and the value in the array, which is a double. So here is an array of doubles. And the code here is absolutely unchanged. So here I've got the max of three things, x, y, and z. Of course, this has a bug. That should be y. But what I'm doing here is the same. I'm just calling them a0, a1, and a2. Of course, the way we invoke the function now also changes. Instead of passing three separate parameters, I'm passing a double array. And the way we can instantiate a literal double array in Java looks like this. So here I'm passing in the array with elements 11, 21, and 31. I'm expecting 31 to be the result. So let's see if this still works. Yes. Okay. So, and the same reasoning applies. I'm doing exactly the same thing going through these three elements. Note that we have two statements here which are identical except for the index. So at this point we have a of 1 on one line and a of 2 on another line. And we can get rid of that commonality. You could imagine we did this for a 4-place array. We'd have 4 lines, or 5-place array, we'd have 5 lines. So we can get rid of that redundancy by using a loop. So what we're doing here is we're initially going to execute this line for I is equal to 1. We'll check to see a of 1. And then we'll do it for a of 2. Okay, so we're doing it for 1 and then for 2. And so we're just doing it twice. So this will now execute here where I is 1 and then where I is 2. Note that we will not do it for the case where I is 3, because 3 is not properly less than 3, and therefore this loop will not execute for the value of 3. Again, the syntax here in Java is to pick in a for loop, we say that I is initially 1. We want to increment I by 1 each time, and we're going to stop when this predicate becomes false. So when I is greater than or equal to 3, we'll stop. Okay, and this runs beautifully. What we've got, at this point though, you can see how arbitrary the choice of 3 is. So the number 3 here feels very out of place. Like, why is 3 here? Why are we only dealing with arrays of size 3? That does seem fairly arbitrary. So what we can do instead is work with an array of any length. And we can do that by using the length field of the array classes in Java. So each array has a length associated with it. And so we can just use that length as our bound. So note that if we have an array with 3 elements, the length will be 3, and the indices for those elements will be 0, 1, and 2. So the way we go through them is something like this. We have a of 0. I can then start here at a of 1. This will go up to a of 2. And then again, once I is equal to the length, the loop will not execute. So when this becomes false, so the index is not properly less than the length, we'll exit the loop. So this is sort of a standard way to go from the beginning to the end of an array. And this function works just fine. And you can see now I can actually use different lengths arrays, and they should work out fine. So here I have tests where I'm going to check a 2-element array, check a single element array. No problems. This should all just work fine. And so we can run it. and it should be fine. Yeah, it's all good. The thing that we've written here is still correct. And I think it's important now to look at it again, that we've generalized to an arbitrary length array just to see what we've done, right? So what's happening is that at each step, we're increasing the number of elements we've looked at by 1. So, and we're using a variable to keep track of how far we've gone. So the variable is called I. And what we're doing here is keeping track of the elements from a of 0 up to a of I minus 1. So at each time through this loop, we've looked at all of the elements from a of 0 up to a of I minus 1. So let's see if that's, I'm going to claim that's true. Let's just check it to make sure that I'm saying the truth. So initially, m is a of 0. So when I is 1, have I really looked at max of a of 0 up to a of I minus 1? Well, yeah, this is, in this case, when I is 1, 1 minus 1 is just 0. So I only have to have looked at one element, which I have. Before the loop even starts, I have looked at a of 0. So it holds at the beginning. And then as I make a step, right, let's suppose I've looked at I elements. Is it true that when I increment I only do that after I have looked at the ith element? And in fact, this is what's happening. So assuming that m is the max of, say, the first 3 elements, now if I look at the 4th element, I can then say after the loop has gone around that I've now looked at all 4 elements. So each time through the loop, I'm adding 1 more element. And then the key here is that when I get to the end, of course, I is going to be equal to a dot length. And therefore, this invariant will tell me that m is the max of the elements from a0 up to the length minus 1. And of course, that's all of them. Okay, so that is all of the elements in the array. And therefore, I can safely say that this is really the max. So what we're using here is what's called a loop invariant. This is something that is true every time before we execute the body of the loop. So the body of the loop here is just line 8. And before we execute line 8, this statement is always true. And it's also true when we exit the loop, which is really very nice. And this is what sort of the reasoning. This is actually, if you look at how you read code, you'll find that if you really understand a loop, you're doing this kind of reasoning in your head. There's no way to understand a loop without doing this kind of reasoning, right? So we have to be able to think about what's happening each time around and generalize it into some abstract form so that we can sort of understand what the loop is doing as it progresses. This code is excellent, and it's handled arrays of arbitrary length. But there's one assumption in the code that makes it a bit brittle, which is that we're assuming that the array has at least one element. So in fact, I can try this on an array that has no elements. And what is this code going to do? So first of all, you might wonder, is this valid Java? And you can see that Eclipse is fine with it. So we can execute. And oh, that's not nice. So what we've gotten here is what's called an array index out of bounds exception. One thing that's wonderful about Java is that when you get an exception, it will tell you exactly where that occurred. So you can see what line it happened on. It happened here. And so you can just click that and see. And it'll tell you, actually, the array index out of bounds exception will tell you that index 0 out of bounds for length 0. So indeed, you can see which test failed because we were actually on in the main program on line 24. So it was actually this test that failed. And that makes sense. So the array has length 0. I'm trying to look at the 0th element. That's not okay. Okay, so, and it's obviously nothing to do with the value I chose here. This is just because I'm looking in the array in this way. In this case, we need to check if the length is 0, then we need to do something. So what do we do? Most beginning programmers will think, well, I'll just do something like this. I'll return 0. Okay, whatever. And this is sort of a solution that does get it to pass. In this case, I have a value. But is 0 a good choice here? I mean, it turns out that 0 is just yet another magic number. It's completely arbitrary. And these kind of magic numbers are just bad. You don't want to have them in your code. They're going to make your code brittle. It's going to break in certain cases. So in this case, what we've done is identify the empty array with the array that just contains 0, or in general, any array that contains 0 as its max. I mean, we could have a bunch of negative numbers and then a 0, and then the max is going to be 0. So having that be the value for the empty array seems kind of wrong. In this particular case, there is a value we could use. It's called double dot positive infinity, or sorry, negative infinity is the one I want. So double dot negative infinity. This makes some mathematical sense if you think of the mathematical definition of max. This is an identity value for the max, but there's many cases where this kind of mathematical identity doesn't exist. And so, there's often just not a good choice for what you should do in this case. So, I mean, you could just say, well, screw it, we're going to throw an exception. And Java's already throwing an exception, so we should be fine with that. But this exception is not very informative. It's giving us the wrong information in some sense. So usually what we'll do is to make it clear that we intend this exception to happen, we'll use a different exception. So in this case, I would put in my documentation that the double needs to be non-empty. So we could add a comment here. This double array cannot be empty. And we can also document this by throwing a particular kind of exception. So the common one for this kind of case is an illegal argument exception. So it's saying that the argument A that you gave me is not a good argument. So so we can run it, the code there. So this is an illegal argument exception. And exceptions are very useful. This is what they're essentially for, is these kind of exceptional cases. That's why they're called exceptions. The mechanics of them is not particularly complex, and I don't want you to get too obsessed with all the details of exceptions. But when you want to, the idea here is to throw an exception and then it can be caught by a calling function. So here I am throwing an exception from max, meaning max doesn't have a good return value at this point. And so it throws that out to the outside world. If the outside world is expecting this exception, it can catch it. So this is the way you do this in Java, is with a try catch statement. So I'll try to call max, not sure it's going to work. And here, if it fails, then I'll catch that exception. In this case, I actually want the exception. So here I'm trying to test the code to make sure it behaves the way I expect. So I'm actually expecting the code to throw an illegal argument exception. So that's what I want. So if I catch the illegal argument exception, I just do nothing. Instead, if the code does not throw an illegal argument exception, then I'm going to be upset. That's not what I want. So in particular, let's suppose we return 0 here. Then we'll fail here because I was expecting the illegal argument exception, not some other thing. So this is a failed test. Here I have a test written, and I can now try and develop the max function. We're going to try and develop it from scratch. So the way I suggest you do this is to start working with an example. So let's work with this example where we have 21, 41, 31, 51, 11. And I suggest that you start sort of in the middle of the process of determining whatever you want to do in this loop. So let's suppose we've already looked at the first 3 characters and we're just looking at the 4th one, which is 51 here. Now, if my loop has already gone through the first 3, I need to have determined stuff about the first 3 in order to know what to do now that I'm seeing the 4th one. And so the process of designing an algorithm here or a loop is to think about what you need to know in order to make progress. So one thing I could certainly determine is the maximum number of the previous 3. So if I know the max of the previous 3, then by just looking at the next number, I can compare this number to the previous max, and I'm good to go. That's sort of the way the algorithm we had worked. So, I mean, one thing is I do need to know where I am. So there needs to be some sort of marker to say, oh, currently I'm on the 4th element, which is index 3. So I need something. The typical name for this is I. So that's for index. So that's my index into the array. So in this case, I would be 3, telling me where I am. And so what I'm actually doing here then is I'm comparing the element at index I. So that's written A of I. And I'm going to compare it to m. So I'm comparing these two things. Oh, wait, what's m? So m, So I need to know the max of all the things I've looked at so far. So at this point, the max would be what, 41? So I need to know what was the max so far. So there needs to be something to hold that. So let's call that m. Okay, and so what I'm doing is I'm comparing the max so far. So if the max so far is less than A of I, then I want to update the max so that it is A of I. So like yay. You know, getting used to the syntax of Java may take you a little while. You'll get used to it. You just need to know where the semicolons and the curly braces go. Okay, so this is the line that actually makes us progress then. So that's great. This will actually look at 51 then and compare it to 41, the previous max, and update the max to be 51. At this point, I have actually looked at A of I, and therefore it's important to make progress. I'm going to update I as well. So we'll increment I by 1. There's lots of ways of writing this in Java. You can write it as I plus equals 1 or just I plus plus. These all do the same thing. All right, so there I have made the body of my loop. All right, so where do I stop? Well, it's important I don't look at A of A dot length, because that is beyond the end of the array, and I'll get an exception if I try to do that. So it's important that I stop when I is equal to A dot length. So I'll continue as long as I is properly less than A dot length. Okay. So now we just need to figure out what these values are. And well, for the value of m, I'm going to assume that the array has at least one element. So we'll take that to be A of 0. And note that I've already looked at A of 0, so I don't need to look at it again. So I'll start I at 1. In fact, so it might be better, this is just fussing around, but so it might be better to write it this way. So m is A of 0. And now I know that I've already seen 0, so I don't need to start there. I'll start with 1 and continue. If you were to write your code like this, where you're actually looking at 0 twice, it would work, but it would confuse anyone who tried to read your code. So unnecessary work is always bad. Not so much because it takes more time or anything like that. It just makes the code harder to understand. So if you're doing something like this, someone who's reading your work would be like, really? Do you need to do that? Why? And so they're going to have a question about it. Whereas if you write it where you're doing only the work necessary, then any reader will immediately understand what you're doing, and they won't be questioning, what is going on in the code. Okay, so there you go. So that's this code in a while loop. So once you've gotten this all settled down and it looks like it's going to work, you need to worry about corner cases. So corner cases are things like empty array. So what if somebody gives me an empty array? Well, poo. I'm not going to be able to work with that. So what I'm going to do in that case is I'm going to throw an exception. New illegal argument exception. There we go. Okay. So that's fine. One thing you'll note is that curly braces are optional in Java for single statements. So I don't actually need a curly brace here. It's not a bad idea to put it in though. So they're not required if you only have one statement inside your if. If you're ever confused about what exactly you think your code is doing, it's always handy to try and format it and see what Eclipse thinks it's doing. You see, Eclipse will actually spread out the curly braces and everything in a certain style. And you can make sure it sort of corresponds with what you think is going on. Okay, so this is nice. There I have a function, and we sort of derived it. And this is indeed the code if you want to see the while loop version of this. Using a while loop or for loop doesn't matter. It's exactly the same. So while loops and for loops in Java are interchangeable. All right, so let's just talk generally about what we just did. So whenever you want to design a loop, what you want to do is pick an example and start in the middle. I think this is the most important thing. Don't start at the beginning, don't start at the end, start in the middle. Assume you've gotten some way through the array, and now you need to make one step of progress. So in order to figure out how to make a step of progress, you're going to have to look and figure out what you need to know. So you almost always need to know where you are, and you need to know something about the things you've looked at. So in this case, we're keeping track of the maximum of the things I've looked at. And so at each step, I'm just looking at a new value and seeing if it's bigger than that previously computed maximum. And so this will tell you what variables you need. So in this case, in addition to the index I need a double M to keep track of the previous max. So once you have that, you can sort of write the body of the loop out. And then you can sort of figure out how it's going to end. So like, where do I stop? And then you figure out how to start everything up, get the initial values, and then you deal with these corner cases. Okay, so whatever they are. One common mistake of beginning programmers is to think that variables always need to start at 0. It's just not true, so don't do it. Starting at 1 often makes a lot of sense. So starting at 2 might make sense depending on your application. Okay, so it's not always going to be 0, your initial value. All right, so that's a general way for designing loops. There's actually many different ways we could compute the max. So I've given you one. It's not the only possible solution. There's other things we could do. So let's think about one of them. I'll just leave this in here because that takes care of this case. But let's suppose that instead of doing things this way, actually let me just get rid of all this stuff. There we go. So, oh, by the way, I need to return the, in the previous code, right, I need to return the max that I computed, not 1. That my test wouldn't catch that for me. Okay, so let's think about a different approach. So what I'm going to say is, all right, let's suppose that instead of knowing the max so far, I don't actually know that, but I do know that none of the numbers I've looked at so far were the max. So when I look at this number then, I just need to see, is it the max? And if it is, I can return it. Yay. If it's not, then I just skip it and go on to the next one. All right, so in this case, you end up with a very different bit of code. So in this case, what I need to do, well, just to refresh your memory. So before, what we were saying is if m is less than a of I, then I was going to set m to be a of I. Right, that's how we were making progress last time. What I'm going to do here instead is to say, oh, okay, well, if none of the previous numbers were the max, then how do I find out whether or not this number is the max? Well, it's pretty straightforward. So let's suppose I'm at the ith number. All right, I'm at number I. And what I want to do then is check a of I. And I just want to see if any number in the array is bigger than a of I. If any number in the array is bigger than a of I, then I didn't find the max. Okay, so how do we do something like that? Well, we have to go through the whole array. So let's use another variable. We'll call it j to go through the array. And to go through the array, it's always kind of the same process, right? Here starting from 0 up to a of I minus 1, the length minus 1. And I'm going to increment j. Okay, so for all of the elements of the array, what do I do? Well, I'm going to see if a of I is, if a of I is smaller than any element of the array, then if it's smaller than a of j, then what am I going to do? Well, I know it's not the max. Well, what am I going to do with that knowledge? I think I need a variable. So let's create a Boolean, something like is max. Initially, we'll say it's true. Okay, so we'll assume that I am the max. And now if I see something bigger than a of I, then I'll say, well, is max is false. Okay, there we go. That should work, something like that. And then after I've gone through there, I can say if is max is true, then I found the max. So I can just return it at that point. I don't need to keep going. I can return a of I. That would be the new max. Okay. Oh, okay, this is interesting. So we need to do this for every I. And so what we're going to do is do this for, what, I from 0 up to I minus, right, up to the length. There we go. So we'll do that for every I. The indentation's gone all wackadoodle. So let's get rid of this declaration. We don't need that. And now let's indent. Oops. Okay. We're starting to look good. And I think, yeah, we're almost making sense. Okay, so let's see. So for any I, so I is going from 0 up through, all the indices. We are going to look to see if a of I is the max. So how do we know if a of I is the max? Well, we'll start off assuming that it is. And if we see anybody bigger, then we'll assume if we failed. Okay? And so if after looking at all the other elements, we know that this is the max, then we're good. So we know it is the max. So we just do this for every element. So we end up with this awkward little error here, though, in Java, which is it's saying that you need to return something here. It's actually impossible for it to get to this point and ever in a program. So as it turns out here, if you think about it, if the length was 0, we've already thrown an exception on line 7. Otherwise, let's suppose we just have a single element. Well, it'll never be properly greater than itself, and so our single element would be the max. Okay. So one thing we can do is just say, well, we can do all this work here, and then we can move this. The error is coming because Java is not smart enough to figure out that you can never get to line 14. So in any case, we can just reverse this so that we go ahead and do this loop at the top. Note that if the length is 0, this body will never execute, and we'll just immediately throw an exception. So it's equivalent code. Does it work? Let's try. See if we got it right. Yeah. Okay, cool. So this is another way of doing the max. And some people would argue this is clear. They're like, yeah, this makes sense to me. I get it. So what I'm doing is just looking at each element and determining whether or not it's the max. And there's a question of like, okay, that's fine. I mean, is this as good as the other solution? Is one better than the other? There's not an obvious aesthetic reason, perhaps. I mean, some people might say, the problem with aesthetics is beauty is in the eye of the beholder. So simplicity, which one is simpler? I don't know. Some people do think about the problem differently. And so sometimes you can make an argument that, this way of thinking about it made sense. We're just going through and we're checking each element to see if it's the max, and we eventually find one. So what's wrong with that solution? Seems fine. So, but in fact, these solutions are not of equal quality. And to understand this, we need to actually think about how long they take to accomplish what they're doing. So I'm going to use a different solution. So we saw that this is correct. So both these solutions are correct. I'm not going to look at them in terms of correctness, and I'm not going to look at them in terms of understandability. Both solutions are understandable, but they have very different performance characteristics. So let me first try the initial solution. So this is my solution that we had initially using a while loop. So here we're just im is aggregating the max so far. And if you run this, what I'm going to do is run it. And I'm going to run it many times, okay? But I'm not going to run it on small arrays. I want to run them on fairly large arrays. So my main program here is going to start at a minimum size of 1,000. And we're going to go up to about 1 billion if we get there. So this is the underscore in numbers just makes them a little more readable. That's 1 billion, that's 1,000. And my main program then is going to start a trial, passing in the size. And then it's going to run a loop where it starts with a 2,000 sized array, going up to the max, up to 1 billion. And each time we're going to be doubling in. So in is doubled. And what we're going to do is run the time trial again with a double-sized array. We just keep doing this with bigger and bigger and bigger arrays. And what I'm going to do is just measure how long it takes to run the max function on an array of that size. So to get an array of that size, I'm using a class that's in your standard library. It's called Array Generator. It will just create arrays for us. I'm going to use array, a particular one, and we can talk about that choice in a sec. So if you, I talk about it now. If you think about the solution we just went through, it'll perform very well if the max is at the beginning of the array, but it's going to do more work if the max is at the end of the array. So I'm actually choosing a sorted array where the max is always going to be at the end. So we'll just see. It is the worst thing we could do for that algorithm. Okay, but first we're going to try it on my initial bit of code and see what kind of performance we're getting. So let's just run this. And what it's printing out here is the size of the array that's in, the absolute time it took. This is the in seconds, how much time it took to do the max function. And then the ratio of this time to the previous time. So what's the ratio? And note that if an array is twice as big, we would expect it to take about twice as long because we have to do about twice as much work. And in fact, you can see this is borne out here. For an array of 500 million elements, I'm taking half a second, whereas for 250 million elements, I'm taking 1/4 second. Okay, and you can see that the ratio here is close to 2. Note that there's a little bit of noise here, and this is just because there's systems effects and other things running on your machine. The noise is very noticeable when you're at small numbers. Small numbers essentially take no time, And so in order to see these kind of performance differences, you need to get large enough arrays where it's taking enough time that you can actually measure it in a meaningful way. So you'll get noise like, here 4, here you get 1. But as things get large enough, usually you'll see some sort of pattern. So this makes sense. About twice as long for twice the size of the array. Let's try this other solution that we have as a candidate and see how it does. So here's my solution where it doesn't indent very nicely here. Let's fix that. Okay, this is the solution where we're determining at each point whether or not we have found the maximum element. So each one, we're just checking it against all of the others. And let's see how it performs. And, oh, this is very different. I believe I had, what, half a billion in half a second? And, oh, wow, I'm up at, wow, 10 seconds just for 128,000 elements. That's not great. So this shows you the kind of performance hit you can get if you write code in an inefficient way. Note that for small values, it probably doesn't matter here. If I had 1,000 elements in my array, who cares? It's going to take not very much time. But by the time we're getting up to arrays of even less than 1 million, this is a quarter million. I haven't even computed it yet. You can guess how long you think it might take based on the kind of numbers you're seeing. You can see it's about 4 times as long every time. And indeed, this is borne out. So it took about 10 seconds to do 128,000. So it's going to take about 40 seconds to do 256,000. So each, for an array twice as big, it takes 4 times as long. So if you remember your high school trigonometry, if you plot that function, you're going to end up with a parabola, quadratic equation. So this is quadratic growth in terms of time on an array. And so this is an objective criterion where you can say, oh, this solution is worse. In fact, there are people that say this is not a solution at all. This is a bug. This is a bug that will show up at some point if you end up getting large enough input. So performance is an important measure or metric for determining the quality of code. Okay, so in conclusion here, when you're reading and writing programs, you need to think incrementally. We think in small steps. That's how the computer works. And so in order to program it, we have to atomize our thinking down to these fine-grained steps. And this, of course, this is the key to being a programmer, is being able to think in terms of making small amounts of progress. We saw how to do that with loops in particular. Loops are very important for programming because almost all programming is done over repetitive tasks. The way you think about loops is using invariants. And they're sort of a key to understanding loops. Even if you're just using them implicitly, they are the key to making progress as a programmer. And finally, performance really does matter. So we're not talking here about, oh, this is just a little faster, a little slower. No, we're talking about dramatically different performance for 2 apparently sort of similar quality solutions. So in this class, we will be emphasizing the correctness of our solutions and the performance of our solutions.